Hi there, in this video we're going to be talking about the binomial distribution. To start off, we'll do a little bit of a thought experiment. So, let's think about this question here. How many ways can we arrange n objects? So n can just be any number. Obviously here n equals 5. Right? So we want to know how many ways we can arrange these 5 different objects. So they could be different colored beads, for example. So if we think about it, the first bead we want to choose will either be the red, pink, orange, yellow, or blue. So we have 5 options for our first bead. So I don't know, let's take the orange one. So that's our first bead. Right? So we have 5 different options for that first bead. But now we've already chosen this orange bead, so we can't choose it again. So now we have 4 options. So let's take the blue one, for example. So now we have 5 options on the first pick, and then 4 options on the second pick. So we can multiply those together because there's 5 possible beads for the first choice and then 4 possible beads for the second choice. And then if we keep going, we have 3 possible beads for the third choice. And then 2. Oops. And then, whoops. Should say 4. And then finally, we have 1 choice for the last one. Okay, so here we have this 5 times 4 times 3 times 2 times 1. And all this can actually be changed to say 5 factorial. Now, 5 factorial just purely means we get 5 and then we multiply, we take 1 away from 5, so we multiply it by 4, and then we multiply it by 2 taken away from 5, and then so on until we get to 1. So that is how many ways we can arrange 5 objects. And we can actually generalize this to answer our question. We can actually arrange n objects in n factorial ways. Right? So in this case, 5 factorial is 120. So we have 120 different ways to arrange these 5 beads. But now, what we're going to say is, what if we have some beads that are identical? So here we have 3 red beads that are identical. Again, n is equal to 5. So now we have these identical beads, it doesn't actually matter which way we order them. So let's say our choice is this order. So what we have here are 3 identical red beads to begin with, and then 2 other beads. Now, the thing is, let me number these. So if this is 1, 2, and 3, if I rewrote this out like so. So you can see that I've rearranged these 2 beads, but we've actually got the same arrangement because all of the beads are identical. So what this means is that any arrangement of these 3 red beads, no matter what the arrangement of the 5 beads in total, in each instance, it doesn't matter what way the red beads are placed. So how many arrangements do these red beads have? Well, there's 3 of them. So as we've learned above, there are 3 factorial arrangements of these red beads. And in total, there are 5 factorial arrangements for the total number of beads. So what that means is that for every single combination, every single arrangement, we want to take out these 3 factorial arrangements of these red beads. And we do that by dividing through by it. So we're counting all of those arrangements, but then we're taking out the ones that are the arrangements of the identical beads. Right? So what that would be is you can write it out like this. And 3 factorial starts at 3. We can cancel these out like so. So we just get 5 times 4, which is 20. So you have 20 possible ways of rearranging these beads. So in general, what we can say is it's n factorial over r factorial ways, where r is the number of identical objects. So you can see here the number of identical objects was 3. So that's our r here. So we have 5 factorial over 3 factorial. And now we're going to say, what if we only had 2 types? Let's do this. So we have 5 objects in total. And then we have, or 5 beads, to be more specific. And then we have 3 red beads, which are identical. And then 2 green beads, which are identical. So what we can say is we can use this rule twice and say we have 5 factorial objects in total. And then we have 3 identical objects that we want to divide by, times by 2 identical objects that we want to divide by. So again, let's write this out like this. And then we get 2 times 1 again. So we can cancel these out once more. And we get 20 at the top over 2, which is 10. So there are 10 ways to arrange these objects or these beads. Now in the more general case, our 5 here is our n. So we have n at the top. And at the bottom, let's call these the number of red beads r. So then the number of green beads will just be the total number of beads subtracted by r beads. So it'll be n minus r factorial. Okay? And then we can say ways where r is the first type, or the number of the first type of object. So in this case, it would be the first type is the red type. And this is actually quite special because this is called, right here, it's called the binomial coefficient. And we can write it like that and say n choose r. And that just denotes this. And we can also write it as NCR, like that. And usually on the calculator, you'll see a NCR button. If you click that and you put your N before the C and the R after the C, you'll be able to work out the binomial coefficient. I'll work it out for you. So yeah, this is a very important coefficient, and it only works when you have a total number of objects split up into 2 types. Okay. So let's do an example on this. So it says, how many ways can you pick 6 lottery numbers from 59? Okay, so let's find our N and our R here. So we have 59 total beads. So our N is 59. And then what we can do is we can assign different labels almost to these numbers. Because technically the lottery balls won't be identical, but we can still group them in with an identical label, such as picked and not picked. So our picked group will have our 6 balls that we've picked, and then our not picked group will have the other 53 balls, right? So here we have 6 and we have 53 here. So then we can just put it into the formula. So we can write NCR. Actually, I'll still do this in green. NCR equals, well, we have an N of 59, and our R, number of objects of the first type, will be 6 then. So we'll have 59C6, and we can put that into the formula for the expression for the binomial coefficient, which will be 59 factorial over 6 factorial, and then our n minus r is just this 53 factorial. And then we'll actually get this absurdly high number. Yeah. And it kind of shows that you probably won't have much luck winning the lottery if you have a 1 in 45 million chance. But yeah, that's just one of the things we can calculate using the binomial coefficient. Okay, so let's do this other example, which will actually tie in to the main thing we're going to be learning about. So it says, I toss a fair coin 5 times, find the probability of 0 heads, 1 head, and 2 heads. So let's start at A with 0 heads. So the only way you're going to get 0 heads is if you get a tails every time. So it will be the probability of tails multiplied by the probability of tails, multiplied by the probability of tails, multiplied by the probability of tails, finally multiplied by the probability of tails. Like that. And what we can say is that it's 0.5, because tails has a half chance, to the power of 5. So we're multiplying it by itself 5 times. And that will give us 0.031. Okay. So that's the chance of getting 0 heads. Now, 1 head, it gets a little bit more complicated. And what I'm going to do is I'm going to write tails as T and heads as H to make things a bit quicker. So in this case, we want the probability of a tails multiplied by probability of tails, probability of tails, probability of tails, multiplied by the probability of heads. Because we want 1 head, right? And this is 1 head. So if you think about that, you'll probably notice that that isn't the only combination. You can have other combinations. For example, your heads could be you could get heads on the first toss. But this is where the binomial coefficient comes in. Now we have 1 head of and then 1 identical object or a head, and then 4 identical objects which are tails out of a total of 5 tosses. So we can use the binomial coefficient to work this out. Or in other words, we will multiply this by all of this by n choose r. Or in our case, it would be 5 choose 1, because we have our n is 5 and our r is h, or the probability of h, or the amount of times probability of h pops up, so 1. because that's the number of the first object we have. And then if we do all of that, we will get a probability of 0.156. And then finally, let's do two heads. So we have probability of tails times probability of tails times probability of tails times probability of heads times by probability of heads. And again, this isn't our only arrangement, so we multiply it by 5, choose 2, because we have 2 heads this time, and that will give us an answer of 0.313. So yeah, that's how we can use the binomial coefficient to really save us time rather than listing out every single possibility. And actually here we would multiply this by 5, choose 0 technically, because 5, choose 0 is actually 1, so it doesn't change anything, but it shows that we have 5 possibilities and 0 heads. But obviously we can omit it because we only have one combination that we need to worry about. So now what we can do is I can generalize this. So here we said it's 5, 0, or we can say n, we'll keep it as 5, 0 times by the probability of tails to the power of 5 times by the probability of heads to the power of 0, because we have no heads, so the power of 0 is 1 and it'll work. And then here we're multiplying it by 5, choose 1. We're multiplying that by probability of tails. This time we have 4 tails involved, so we will put it to the power of 4, and then the probability of h will just be to the power of 1. And you can see I'm just simplifying this, so instead of writing p, the probability of tails 4 times, I'm just putting it to the power of 4. And then here we have 5, 2 times by the probability of tails, power of 3, times by the probability of h to the power of 2, like that. And you can potentially actually even spot a pattern here, that we can actually figure out what the probability would be to get 3 heads and 4 heads and so on, using this formula, which is, if I write this right, probability of r successes in n trials is n, choose r, times by probability of success to the power of r, times by probability of failure to the power of n minus r. So in this case, our 5, choose 0 is just this, n choose r, our n is 5. I'll do this in orange. Our n is 5, our r will just be 0, 1, 2, etc. Our probability of success is at our heads, and our probability of failure are tails. And then again, this is 0, 1, 2, and then this will be n minus r, so if r is 0, it'll start at 5 and then go down. And you can see that's exactly what's happened. So our failure is tails, and that's been going down 5, 4, 3. Our probability of success is r, so it's been going 0, 1, 2, and then this has been changing 0, 1, 2, and this has stayed at 5. So this is actually a binomial distribution function. Here it is. And in a more general case, it's this. So if you remember when we were learning about random variables, we learned that the probability distribution function for a random variable x is denoted by that. But this is a special type of binomial, a special type of probability distribution function, and it denotes a binomial random variable. And you can see it goes basically along the same lines. The only difference is that instead of r, we're using x, and instead of success and failure, we're using p as the probability of success. Here it says p is the probability of a success. So that's the same thing as p success, and we're using 1 minus p as our probability of failure, because if you don't succeed, you fail, so it'll be 1 minus p. And generally, we write a binomially distributed random variable, as this, where n is the number of trials, so it's the n that we looked at here, and again, p is the probability of a success. And also, the expected value of a binomial random variable is NP. So that's also an important result you should know. So let's do this example. I roll a fair 6-sided dice 5 times. Find the probability of rolling 3 6s. What is the expected value of 6s? Okay, so let's distribute this binomially. First, let's create a random variable that denotes what we want. So let's say x is a random variable that denotes the number of 6s, because that's what we want to find out. So then we can model this x with the binomial distribution, and our n in this case is, well, we're rolling it 5 times, so it's 5 trials, and then the probability, well, is just the probability of getting a 6, so that will be a 6th, like so. So now what we can do is we can use the distribution function. So we get x equals, and the one we want is 3 6s. So then we just use this formula here, substitute our values. So our n is 5, our x is 3, our probability of success is a 6th. We multiply that, we put that to the power of x, which is 3, and then we multiply that by 1 minus a 6th, which is 5 over 6, and n minus x, which is 5 minus 3, which is 2. And if we've worked that out, we will get, or more specifically, we'll get this, which is the binomial coefficient, multiplied by 1 over 216, multiplied by 25 over 36. And that's what we've done, is we've put this in the we've put this binomial coefficient into this form, and we've just we've taken out the powers and we've calculated these, and we'll get 0.032. So that is the probability of getting 3 6s. And the expected value of the 6s, well, that's n times p. So n is 5. So we can write the expected value like this if we wanted to. And that's 5 times by a 6th, because that's n and that's p. And then we'll get 5 over 6. So you might be thinking, how can the expected value be 5 over 6 if you can't get 5 over 6 6s on a dice? But that's but really, finding expected value is just seeing mathematically what is the most likely option, or what's the most likely outcome. It doesn't really take the context into account. But you can see that's why our probability here is so low, because getting 3 6s is just so far away from not even getting 1. So yeah, let's move on. There's actually 5 conditions to the binomial distribution. If all of these conditions have to be met, if they're not, then it can't be distributed binomially. So our first condition is that there's a fixed number n of trials. So the number of trials can't change or isn't ambiguous. Okay, second one is each trial results in success or failure. Yeah, so you only have 2 options for each trial. So you can either have one option or the other. You can't have a third option, for example. Okay, the third thing is that all trials are independent, and you should have learned about independence when you were learning about probability, and it just means that none of the trials can affect the outcome of future trials. The probability of success P is the same in each trial, so the probability doesn't change. And finally, I can get rid of this. The variable in the total amount of successes the variable is the total amount of successes in the n trials. So you can get questions that tell you, or that ask you, if a particular set of trials can be distributed binomially. And sometimes you have to pick out what won't work. So let's read this. So I will toss a fair coin until I get 4 heads. Can this be distributed binomially? Right? So we're just asking whether this can be distributed binomially. We're not asking to being asked to calculate anything, for example. It also says assume independence, and a lot of questions will tell you if trials are independent. So what we can say is we can actually tick this one off, because it tells us that the trials are independent. Okay, so let's look at some of the other ones. The variable is the total amount of successes in the n trials. Well, we're actually not given a variable yet, so this one we can tick off because we haven't really been given a variable. So here, this one says the probability of success is P, or success P is the same in each trial. Well, it's a fair coin, so each trial will be the same probability of a half, so that one gets ticked off. Each trial results in success or failure. Again, yes, we can attribute heads to success and then tails to failure, so that works. But this one, there's a fixed number n of trials, doesn't work because we have 4 heads. It says we will toss a fair coin until we get 4 heads. But the thing is, we don't know how many tosses that will take to get to 4 heads. It could be 4. They could just get 4 heads. It could be 100 if they're particularly unlucky and they keep getting tails. So this one doesn't work. So we can say no, since there's not a fixed number of trials. So yeah, it's really good to understand each of these and to use them to figure out whether the binomial distribution will work in a specific set of trials. And it also just gives you a better idea of what you should look for, especially later on we'll learn about the normal distribution. It's important that you can distinguish between the two. So this is a good set of a good set of rules for you to make sure that you know which is which. Alright, to finish off, let's look at the binomial cumulative distribution function. Now, if you remember the normal cumulative distribution function for general random variables, it looks like this. So it's the probability of x, a random variable, being less than or equal to a certain value of x. But we can also use this with the binomial distribution. And we can find out how in this example. So example 5 says a biased coin has a probability of 0.35 of being heads. Find the chance of A, getting fewer than 3 heads, getting more than 5 heads, getting between 2 and 6 heads when tossed 12 times. So first off, let's just define our random variable. Let's say x is the number of heads, and then let's distribute that binomially. We have 12 tosses and a probability of 0.35. And we can also look back and see that all of these conditions are met. We have a fixed number n trials. 12 trials and a fixed probability. This question, it hasn't said that they're independent, but you can assume that they're independent because when you toss a coin, usually the trials are independent. What else? Our variable is the total number, is the total amount of successes, because it's the amount of heads, and if we attribute heads to successes, then we're okay. And finally, we're tossing a coin, so our heads is success and tails is failure. We only have 2 outcomes. Alright, so now we know it works as a binomial distribution. So we can start with A. So, getting fewer than 3 heads is x being less than or equal to 2, isn't it? Or it would be less than 3. That's fewer than 3 heads, isn't it? But the thing is, what we always want to do is we want to get it into this form. This is the form we want. X is less than or equal to a value. So we can write the same thing. We can write this the same way by writing it like this. Because this is taking all the values less than 3, so that's 1 and 2. But if we put less than or equal to 2, well, that still gets 1, but it also equals 2. So we'll get the same thing. Okay? So this is the probability we want to figure out. So we know that this also equals the probability of getting no heads plus the probability of getting 1 head plus the probability of getting 2 heads. Okay, so all I've done here is I've used the formula for the probability distribution function here on these 3 values, x equals 0, x equals 1, x equals 2, because those are all the values less than or equal to 2. And then we get this as our final probability. Obviously, that is a lot of work, and that is actually quite a small amount compared to what we could get. For example, I'll show you in our second question. It says, what's the probability of getting more than 5 heads? So that's the probability of x being greater than 5. But remember, again, we want to get it into this form. So let's put it as 1 minus the probability of x being less than or equal to 5. So this is the same form, but all we've done is we've taken the opposite probability. So we have 5 here, and then we have 6, 7, 8, 4, 3, 2. And greater than 5 is all of these. But what we're taking is everything less than or equal to 5, which is this. So the probability of all of these, and then we're taking it away from 1, which will actually just get rid of all of these probabilities and only give us these. Because the total probability is 1. So that's how that works. But now we've got it into this form. And the reason we've got it into this form is that you can put it into your calculator or use a binomial table to figure it out, but you need to have it in this form to figure out that value. So the way you can figure it out on your calculator and binomial tables, I'm not really going to go over, but I am going to link some videos in the description which will do that for you. So if you don't know how, quickly watch those videos, and then you can come back and you'll understand how I'm getting these values. So if I put this into my calculator, I'll get 1 minus 0.7873. Or in other words, 0.2127. Like so. And that will give us the probability of x being greater than 5 without having to do all of this calculation. And then now we want to get between 2 and 6 heads inclusive. So that will be the probability of x being in between 2 and 6, like so. Now, how do we figure this one out? We want to get into forms like this. Well, what we can do is we can actually split this up and say the probability of x being less than or equal to 6 minus the probability of x being less than or equal to 1. And again, I'll show you why that's true. So, what we're doing here is we want these values here. So all we're doing here is we're getting the probability of x being less than or equal to 6. So all of these, and then we're subtracting the probability of being less than or equal to 1. So we still get this value because we're taking this bit off of here. So we only get these values. So I just erase these. We can also figure out these two probabilities on our calculators or using a binomial table. Bear with me. So on this one is 0.9154 and this one is 0.0424. And if we calculate that, we get 0.873. And that's our probability. And it makes sense that it's so high because it kind of lands very much in where you'd expect it to be. In fact, the expected value would be 0.35 times by 12, which is 4.2, which lies basically in the middle of this inequality, or in between here. So it makes sense why that's such a that's 87%. Alright, so have a go at these exercises. 2B is quite difficult, so that's a challenge question. Thanks for listening.